Hello. Let me know when you can see and hear me, please. Hi, hi. Hello. Hi, Amani. Hello. Don't mind me. I'm just fighting with my green screen. Hi, hi, Chinwendu. Hi, Amani. Do we have anyone else in the chat? If there's anybody over on TikTok, if you want to talk to me, okay, and actually ask me questions, you have to be over on YouTube. So the link is in my bio to go over there. Okay, but for now, today, rather than an ask me anything, we're going to focus particularly on Hess's law and energetics by special request. Okay, so we will start with some definitions. Okay, because, and as I always say to my year 13s, Chinwendu, you'll know this, the definitions in energetics and thermodynamics are everything. So we'll start with standard enthalpy change of formation. So that is our, what's that? That's the enthalpy change when, feel free to give me an answer in the chat. Again, if anybody over on TikTok wants to give me an answer, please come over to YouTube and then I'd love to see your answers. Oh, the enthalpy, I'm missing out words. The enthalpy change when dot 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 1 mole of a substance. You can say compound, but technically elements have enthalpy changes of formation too. They just happen to be 0. Okay, fantastic, lovely, great. Chinwendu is formed from its elements under standard conditions. Lovely. I'm just going to write SS. All reactants and products in their standard states. Oh wait, that should be SC. Let me just write the words. Let's not take any shortcuts until it's time to take shortcuts later on. Lovely. In their standard states. So for example, if we wanted to write the equation for the standard enthalpy change of formation for, I don't know, you can give me your favorite compound. Let's keep it simple. Let's say butane. Okay. So we'd be making 1 mole of butane, which is a gas. And that would be formed, okay, sorry, Chinwendu, NH3 is a good one too. That would be formed from its elements, so 4 lots of carbon and 5 lots of hydrogen, making sure that we've got their standard state. So for carbon, the standard state is solid, but more specifically solid, oh, hello, graphite. And then for hydrogen, that would be gas. Okay. For enthalpy change of combustion, that is our standard enthalpy change when, hi Krish, welcome, welcome. You're getting a preview into A-level chemistry. The enthalpy change when, let me just change the color so that we can see it. Yeah, Krish, there are some year groups still have lessons on Fridays. I think year 9 and 10 doesn't have lessons on Fridays. Okay, so the enthalpy change when 1 mole of a substance burns in excess oxygen, or you can say undergoes complete combustion, same difference. Again, under standard conditions, all reactants and products in their standard states. Okay, so the end part, this part is the same for both, and this part is the same for both as well. It's just a case of what is happening to that substance. For formation, we're making or forming that substance. For combustion, we are burning that substance. So if we took, let's take butane again, because why not? It's already there. If we wanted to write the equation that goes along with the standard enthalpy change of formation for butane, we would have C4H10 plus oxygen producing carbon dioxide and water. Oh, a couple of questions in the chat. I'll answer those as soon as I'm done with this equation. Everything would need to be in the standard state. So gas, 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 and liquid. And then balancing that, 4 carbon dioxides, 5 waters, and then we balance our oxygens accordingly. So we might need a fraction for this. We've got 8 plus 5 oxygens on the right, so 13, which means that we'll need 13 over 2 oxygens. And we cannot double that, okay, because by definition, we can only be burning 1 mole of our substance. Okay, Krish, there's no GCSE drop-ins yet, okay, but going forward, we'll start to do GCSE drop-ins as well as A-level ones, okay. Sufyan, how private candidates would apply for exams? Oh, that's a good question. I don't have the details on that, Sufyan, but I'm sure if you go to the AQA website and then go to the candidates private section, it will tell you how to do that. Okay, but essentially you'll need to find an exam center. Okay, bye, Krish. I'll see you next week. Well, I'll see you in the chat next week. Okay. So we're going to apply this to Hess's law, okay, again, because lots of A-level students find this quite tricky, but it can actually be really straightforward. I was going to say it's one of my favorites, but I say that about everything, so I'm trying to stop myself from saying that about everything. So Hess's law essentially tells us that the enthalpy change, lovely Chinwendu, the enthalpy change is independent something along those lines, lovely, of the route taken. You don't necessarily need to know this off by heart, but you should understand the concept of Hess's law, right? Which is essentially that, let's say if we have a chemical reaction where we are trying to go from A to B, and we want to know, lovely, hi Dave, thank you. And we want to know what the enthalpy change for this reaction is, but we can't figure that out directly. We can go indirectly. So we can instead go to something that's C. So going from A to C and then from C to B would be the same. So delta H1 plus delta H2 will be the same as delta HR. Okay, so the overall enthalpy change, as long as you're starting and ending in the same place, it will be the same. Okay, so hi King, sorry I missed, oh hi King from last week, yay, hi. Okay, let's start to put this into practice. Any questions, please do, absolutely, please do put them in the chat. And also a quick plea, I am on Instagram, I am so close to having 50K followers. And if there's anyone in this stream, whether on TikTok or YouTube, that wants to push me over the edge, it would really make my day / week / month / year. Okay, so let's start to put this into practice. There are 2 main types of Hess cycles that you'll see in A-level chemistry. Okay, they're not the only ones, but they're the main ones that you'll be assessed on. So the first is enthalpy of formation, which we saw in our starter with our definitions. So that's when we're forming a substance from its elements. Okay, so if we were to construct a thermodynamic cycle or an enthalpy cycle, enthalpy diagram, we would start with our reactants. Oh, Chinwendu, no Born Harbor today, but we can do that in a future session. These are quite like short, punchy sessions, so we kind of focus on just small parts of topics at a time. Okay, but we can definitely go back over Born Harbor cycles, or you can watch the recorded videos from our September module, right? Lovely. So reactants to products. But again, let's say we can't figure out that enthalpy change directly. So if we're given enthalpy of formation data, then we can go via the elements. So we can put the elements down here at the bottom of our cycle, of our diagram. And so going from the elements to the reactants, that would be the enthalpy change of formation for the element, for the reactant, sorry. Okay, King, how did you find it? And then going from the elements up to the products, that would be the enthalpy change of formation for the products. Okay, notice the arrows have to point up because they're going, by definition, we're forming the substance, so forming the reactants or the products from the elements. So the arrow needs to go from the elements to the reactants, from the elements to the products. Okay, so now if we wanted to calculate the enthalpy change of the overall reaction, so this that we're trying to find out, again, going from the reactants to the products, the enthalpy change is independent of the route that we take. So if instead of going directly, we go indirectly, so we go down here and then up here, that will end up giving us the same. Okay? But if we flip an arrow, then we're going to flip the sign of the enthalpy change. So this would be the negative of the enthalpies of formation for our reactants. And then this arrow, it's following in the same direction that it was before. So that would still just be the enthalpy change of formation for the products. So the overall enthalpy change for this reaction is the negative of the enthalpy change of formation for the reactants plus the enthalpy of formation for the products. Or the nicer way round to put this, because we don't really want that minus sign first, that is the same as the enthalpy change of formation for the products minus the enthalpy change of formation for the reactants. Okay, I'm going to put this in a, actually, I'm going to highlight it. Oh, very exciting. I'm going to highlight this very neatly. Absolutely, Dave. Products minus reactants. Because if we understand where this is coming from, then whenever you're given enthalpy of formation data, you don't actually have to draw a whole Hess cycle to figure out what's going on. Instead, oh, sorry, what's going on? Instead, we can just use this expression directly. So we can just say directly, enthalpy change of formation for products minus enthalpy change of formation for reactants. That's your enthalpy change of reaction. Okay. Oh, Nolix, good question. I don't know much about the Singaporean qualifications. If they're called A levels, then it's probably the same. Unless it's called the international A level, then the specification is slightly different. Okay, and also depends on which exam board you're on. No, 4:30. No, I have like a scheduled course lesson at 4:30, so we're at lunchtimes. 1 p.m. for now. Again, might switch around as we move forward. Okay. Oh, Dave, not at the moment, but that's a good idea. That's a really good idea, Dave. So watch this space. Okay. Nolix, yeah, if it's just called GCSE A levels, and it's the same as the UK, as far as I'm aware. But please correct me if I'm wrong. So let's put this into practice. Okay. We've got this. Let's go back to a pen, please. Okay. This is a reaction. This is our reaction. Propanol plus blah, 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 trying to form some stuff, okay? And they've given us already the overall enthalpy change for this reaction. They've given us some of the enthalpy data, and we need to find out the standard enthalpy of formation for propanol, which is one of our reactants, okay? Ian, what do you mean? What's a bit late? And hi. So because we know without having to draw our cycle that our enthalpy change of reaction is equal to the enthalpy of formation for our reactants minus the enthalpy of formation for our products. Hang on, no, it's not. How embarrassing. Rewind, brrr, okay? As we all know, the enthalpy change of formation, enthalpy change of reaction is equal to the enthalpy change of formation for the product minus the enthalpy change of formation for the reactant. And that's definitely what I said the first time round, okay? So we can now start to substitute in the values that we actually have, okay? So the enthalpy change for the reaction we are already given in the question. So that's minus 114. That's going to be equal to the enthalpies of formation for our products. Our products are chloropropane, 1-chloropropane, and H3PO3. So that would be 3 times minus 130. So 3 times our chloropropane plus our H3PO3 minus the enthalpy changes of formation for our reactants. Our reactants, we don't actually have our we don't have our propan 1 yet. That's what we're trying to find out. So we'll just say 3 times our formation of that we're trying to find of X plus our formation for our PCl3. Okay, then, and we don't necessarily need to put all the numbers in for now, because the key here and what I really want to focus on, seeing as we are limited in terms of time, is now we just take our calculators, which I know that you've all got in front of you, right? And then we just solve for this term. Okay, we solve for that term, and then once we've got that term, we will then divide by 3 to get our final answer. Okay. We can talk about shapes of molecules in a future stream, so that's a great idea. For now, we are just looking at Hess cycles. That's our focus for today. Okay. And to answer your question from before, the Olympiad, the Chemistry Olympiad, it's a competition run by the Royal Society of Chemistry that you can do in year 12 and 13. It's designed for year 13 students, but you can do it in year 12 as well. And you can get, a certificate that says, yeah, great, I'm happy. Okay. Patrick, you would get chlorination. That would be electrophilic substitution. So you'd make chloromethane. That would be alkylation, sorry. So you would end up with methylbenzene, Patrick. Okay. Lovely. If anyone wants to solve this and give me the answer in the chat, feel free. Okay, but for now, the key is, can we figure out what to do with this data when we're given it? Oh, shift solve. If you've got a fancy calculator, then you absolutely could do that. Yeah, I don't have a fancy calculator. I have just a basic calculator. Okay, so I would have to go through and put all of these numbers in. I'd go, okay, so minus 390 minus 972 minus 3x minus 339, and then I'd start moving numbers around. Okay, feel free to put the answer in the chat, but for now, as long as we are happy with the process, hi Timo, welcome, welcome. As long as we know the process, let's move on to our next example, okay? Because otherwise we won't have time to do more than a couple of questions, okay? Now, if instead of enthalpy of formation data, we're given enthalpy of combustion data, then because combustion, we are burning in excess oxygen, we will end up with combustion products. Okay, so we can start to set up our Hess cycle in exactly the same way. So we start with our reactants. We're going to our products. And we want to find out this enthalpy change of reaction, but we can't do that because for whatever reason, we can't do it. Okay, but if we're given combustion data, then we can complete our Hess cycle by including the combustion product as the indirect pathway that we're going to go by, the indirect route. And typically, let's say if our reactants and products contain carbon and hydrogen, our combustion products are typically going to be carbon dioxide and water. Okay, 9.9 times out of 10 at A level, we do this when we're dealing with organic compounds, and so carbon dioxide and water will be our combustion products. Again, based on our definition, and you tell me please in the chat, based on our definition, what direction will our arrows point in from the reactant, between the reactants and products and the combustion products? What direction will our arrows point? Any suggestions? Anyone? Hello, hello, hello. Oh, okay. So again, by definition, enthalpy of combustion, standard enthalpy change of combustion is when we are burning 1 mole of substance in excess oxygen. So that means we're going from our reactants burning in excess oxygen to give us our combustion products. And then same here, we'll take our products, burn them in excess oxygen to give our combustion products. Okay, so it's the opposite way round to formation. For formation, it was from the elements up to the substance. For combustion, it's from the substance down to the combustion products. Okay, once again, we can label these arrows. This first arrow, this would represent the enthalpy change of combustion for our reactants. And this arrow rather would represent the enthalpy change of combustion for our products. But again, we need to find out our route. So we need to go from the reactants to the products in an indirect way. So what do we have to do? Well, we have to go first down and then up. Okay? Remembering, if we're following an arrow exactly as it was before, it stays the same. But if we flip an arrow, then we flip the sign. Okay, so this arrow, the first one, still just represents the enthalpy change of combustion for the reactants. But this second red arrow represents the negative of the enthalpy change of combustion for the products because we flipped the direction of the reaction. So putting that all together, what do we end up with? Enthalpy change of our reaction, so this enthalpy change here, is equal to the enthalpy change of combustion for the reactants minus the enthalpy change of combustion for the products. I'm going to highlight that again. Oh no, don't do that. Highlighter, not red, scary. There we go. Okay, so when you've got formation data, it's products minus reactants. When you have combustion data, it's reactants minus products. Okay, if you want to make up a nice acronym that helps you, you're more than welcome to. So for example, oh, where's my pen gone? Oh no, I've lost it. Oh, because it's yellow. Okay, so for example, you can say formation is products minus reactants, combustion is reactants minus products. So whatever mnemonic, okay, you might want to use to help you remember, then feel free to do that. Ooh, how to maximize Christmas holidays. I would say book in some time where you are absolutely, categorically going to do absolutely nothing. Okay, so make sure you've got at least a few days that you've already scheduled out to do absolutely nothing, because the worst thing is taking a break but feeling guilty about taking that break. So schedule in your breaks that when you're taking it, you can literally look at your calendar and go, oh, I'm meant to be taking a break right now. Wonderful, fantastic. Okay, so schedule that time in, okay, and stick to that time. And then your other times fit in review and practice of the topics that you've done so far. Okay, it's like a reflective cycle. So you'll review something, you'll answer some questions, you'll mark it really harshly, you'll see what you need to recap, and then you'll review that again, and then you'll just keep going round and round and round until you're not making any mistakes anymore, ever, ever. In theory, hopefully, eventually. Okay. Let's do a practice question for enthalpy of combustion. Yeah, definitely lock in at Christmas. But again, please give yourself a break. If you don't, you'll come back in January just burnt out and not ready to take in what's happening then. Okay. So use the data. Oh, it's not a table. Use the data below to calculate the standard enthalpy of formation of liquid methylbenzene. Hey, methylbenzene, Patrick, are you psychic? Okay, so here we haven't been given an overall equation that we're trying to find the enthalpy change for, except we have, because they've given us the equation in words. They've said we want the enthalpy change for the standard enthalpy of formation. So we need to write that equation ourselves. Does anyone want to have a go in the chat of writing that equation for the standard enthalpy of formation for methylbenzene given our definitions from before? Hi, gaming fan. Hi. How are you? You're getting a bit of a, as I was saying before, an insight into A-level chemistry. So standard enthalpy of formation, forming 1 mole of our substance from its elements. So we're going to start with the elements, carbon and hydrogen, and then that's going to produce our methylbenzene. Okay, of course, everything needs to be balanced. So 7 of these and 4 of these, and everything needs to be in their standard states. So solid, gas, liquid. So this is the enthalpy change that we're trying to figure out. But in the question, they've given us the enthalpy of combustion. So because they've given us combustion data, that means that we're going to use CRP, combustion. We'll do reactants minus products. Ariba, this is for all exam boards. Any exam board, you'll be expected to do this. Okay. So our enthalpy change, delta H, that we're trying to figure out is equal to the enthalpy change of combustion for our reactants minus the enthalpy change of combustion for our products. And we know that we're using this expression because they've given us combustion data in the question. Okay, if they give us combustion data, we use this approach. If they give us formation data, we do products minus reactants. Okay, so now we just substitute our values in. This is actually quite nice and easy in theory, right? So enthalpy changes of combustion for our reactants, that's going to be 7 lots of our carbon. So 7 times minus 394 and 4 times minus 286. And then we're going to subtract the enthalpy change of combustion for our product, which is C7H8. So minus 3909. And when we plug all of those numbers into our calculators that I'm sure lots of you are going to do for me and tell me the answer, maybe we will just get our final answer, and that's it. Okay, Adam, this is for our energetics 1. So enthalpy changes, specifically Hess's law. Okay. So again, quick summary. If you're given formation data, then we'll use our expression delta H is equal to our formation of the products minus formation of the reactants. And if we're given combustion data, then we'll use the expression combustion of the reactants minus combustion of the products. Okay, A got 7. Let's see, does anybody agree, disagree? Now I really want to know. Oh no. Let me see how quickly I can do this. Anyone with a fancy calculator? Oh, me too. So minus 3902 minus 3907. Yeah, lovely. This is for the course, Adam. So this is for the A-level course. So this is just like a bonus practice lesson for everybody. Yeah. Okay, last week and the week before, we focused a lot more on organic, but today we're focusing on Hess's law. Next week, we've had some requests already for inorganic chemistry, so we'll go there next. And then depending on what people are asking for, we'll make these drop-in sessions on whatever particular topics you are most worried about or need the most help with, or they can be more open where you just ask me any question. Okay, so they'll vary from week to week, specifically what we might be covering. Okay, now, do you want to do a couple more? A couple of weird ones, but they're really nice and they're often multiple choice, even though I haven't given you multiple choice. Okay, yeah, inorganic is one of those ones. You have to keep reviewing it because there's a lot of content. Okay, and so if you don't review content, it's going to disappear. Okay, Patrick, do you have a particular question? Otherwise, I really cannot help you. Okay. In the last few minutes, let's do a couple of these types of questions. These are my favorite, okay? And I call them, and your maths teachers might shout at me for calling them this, but I call them like simultaneous equations type ones, okay? Because I'm with you, Ian. Moles, oh my gosh, I haven't shown you my hat. Before we go into the explanation, I need to show you my hat. This is how important moles are to me. Very, very important. Okay. Right. So if we are given the enthalpy changes for a couple of reactions, and then we're asked to find the overall enthalpy change for another reaction, we can kind of, yeah, it was a present for my year 13s last year. Oh. So we can kind of like switch, reverse, and scale up the equations as needed to give us the overall equation, okay? Because the direction of the reaction will give us the sign of the enthalpy change. And if we scale it, then that's also going to scale the enthalpy change. So let's do this one here. We want the enthalpy change for methane, giving us carbon atoms and hydrogen atoms. If we look at our two equations above, I'll call this equation 1 and equation 2. All we need to do is look at how these equations relate to the final one that we're trying to get to. Okay, so if we look at the, we can look at the carbon, okay? The carbon in the first equation is on the left-hand side, it's a reactant, but in our final equation, it's on the right-hand side, it's a product, which means that we would need to flip the direction of this reaction. And if we flip the direction, then we have to flip the sign of our enthalpy change. So we'll multiply by -1 to flip the sign. Okay. For our second one, we can't look at the H2, but if we look at the H, we have got 2 H's on the right-hand side. Okay. Now, in the equation that we're trying to get to, the hydrogens, they're on the right-hand side, but we've got twice as many, which means for this second equation, for it to add up to match this final equation, we're going to need to multiply this by 2. Okay, we can't look at the H2, great question A, because the H2 is not in our final equation that we're trying to get to. Okay, we're trying to organize these equations in a way that when we add them up, they'll give this overall equation, and anything that's not in this equation will cancel out. Okay, so the H2s, once we've flipped this and we've doubled this, they'll cancel out because they're not in our final equation. Okay, so the overall enthalpy change for this equation is going to be equal to the negative of the first one, because we had to flip the sign. Sorry, let me not swear at you. Because we had to flip the sign. So that would be positive 75 plus double of our second equation, because we had to multiply our second equation by 2. So plus 2 times 436. And that will give us our final answer, whatever that is. Let me do it quickly. Or if anyone can do it quick, actually, no, you can't do it quicker than me. I mean, you can, but I've just done it already. 947 kilojoules per mole. Okay, let me know if you agree with me. Ooh, being true, great question. How is it actually prepared? You can see the structure using X-ray crystallography, or like elemental analysis. Okay, lovely. Alia, A. I'm glad that you agree. Let's do a couple more. I have to stay for an extra 7 minutes. Let's do 2 more because I've got 2 more prepared and I kind of want to do them. Okay. Next one, again, using the same approach. We have got 2 reactions. We want to calculate, lovely, the enthalpy change for this reaction. So now we need to see how do reaction 1 and reaction 2 contribute to our final one. So we can see what we need to flip, reverse, and scale to give us our final enthalpy change. Okay, so for reaction 1, what might we want to look at? What should we look at from here? Which species, which substance? Any suggestions? Any suggestions? So, oh, okay. So we can look at the NH3 or we could look at the H2O. Absolutely, A. I'm going to just look at the NH3 because it's the first thing here. We have got 4 NH3s on the left-hand side. And in our final equation, we've got 4 NH3s also on the left-hand side. 6 waters on the right, 6 waters on the right, which means our first reaction, we can just keep it exactly as it is. We don't need to do anything to it. It's already going in the direction and in the scale, essentially, that we want it to be. Okay. Now looking at reaction 2, what should we look at? Indeed, A. What should we look at for reaction 2? We've got 3 options. Which one should we choose? Oh, so I wouldn't look at the O2 for this one. I would only look at the NO2. The reason that I don't want to look at the O2 is because the O2 is in both equations. Okay, so just scaling it in one equation isn't necessarily going to give us the answer that we want. So ideally, look at something that is only in that equation and not in the other one that we're trying to figure out. Okay, so I'll look at the NO2. The NO2 is on the right-hand side, and it's also on the right-hand side in our final equation, but we've got twice as many, which means reaction 2, we can keep it going in the same direction, but we're going to have to multiply it by 2. Okay? And again, anything else that's involved in these reactions, all of the other substances, they'll cancel out. Okay? Absolutely A. So for our enthalpy change, that's going to be our reaction 1 enthalpy change, so minus 909, plus 2 times our second enthalpy change, so 2 times minus 115, and that's going to give us our answer. I'm sure you're going to tell me what the answer is. Please do. And then I'll see if I agree. Minus 1. Yeah, A, I agree. Lovely, Alia, I agree as well. Wonderful. Great. Last one. Last one. Trickiest one. Calculate the standard enthalpy of combustion of butane from the data below. So this time, they haven't given us the equation, but they've told us that we want it for the standard enthalpy of combustion. Because we know the definition of the standard enthalpy of combustion, we need to write that equation ourselves. Okay? So for the standard enthalpy of combustion, the equation that we want is butane. Oh, did we do this right at the beginning? Yeah, butane plus oxygen producing carbon dioxide and water. Okay, balancing this, 4 carbon dioxides, 5 waters, 8 plus 5, 13, 13 over 2 oxygens. Okay, so this is the equation now that we're trying to get to. We had to write it ourselves because we are expected to know what this means. And now the rest of it is just as straightforward as the other ones in theory. Oh, let's see. This time we've got 3 equations, but hopefully should still work out in the same way. For our first equation, what do we want to look at? Let me label these. So for equation 1, what do we want to look at? Lovely, great A. We want to look at the CO2. It's already on the correct side, but we don't have enough of them. So we're just going to multiply that by 4. Lovely, Ailey, as well. So multiply by 4. For our second equation, we want to look at the water, right? And again, it's already on the correct side, but we know that we're going to need to multiply that by 5. Lovely. And then for our final equation, we'll look at our butane. Fantastic. What will we need to do to our final equation to get it in the way that we need to get it? What will we need? Lovely, times -1 because it's on the wrong side of the equation, but it's the right scale. Fantastic, yay. So now our enthalpy change is going to be equal to 4 times -394 plus 5 times -286 plus -1 time plus 126, right? Because we've taken the positive of it. And then we get our answer. And as your parting gift to me, please tell me what that answer is. I agree. Yeah. Wonderful. Excellent. Great work. Okay. We will be back next week. Again, keep an eye on Instagram, keep an eye on TikTok, so you know the times for the live stream next week, Friday. It'll most likely be at the same time, but just in case it changes, you'll be able to see the details there. And if you want to sign up to my newsletter, so that you know all of the different TikToks that link to what we're studying, then again, look out on TikTok later on. I'll be putting the link. Actually, no, you can get the link directly from my TikTok already. Okay, so from the link in the bio. Okay, for now, yay, I'm glad that you enjoyed it. And I will hopefully see you next week. Anyone that is on TikTok at the moment, thank you for joining. Next time, come over to YouTube so you can talk to me. Okay, join the fun over here. For now, have a lovely. You can never click on the links. Oh, oh, that is unfortunate. Try maybe on my Instagram instead. The link will be directly in the story, so you might be able to click it over there. Okay, I'm not sure why either. Okay, have a lovely rest of your Friday, lovely weekend when it arrives. Yay, Ian, thank you. And I'll see you hopefully next week. Bye. Bye.